All right, let's begin the second argument of the intelligent design movement, and that is specified complexity. All right, many times we will tell people that life is too complex to have evolved. So now with these intelligent design arguments, hopefully you have a way that you can explain what you mean by that. Living things are too complex to have evolved at all, but especially by numerous, successive, slight modifications. So specified complexity is different than irreducible complexity. So what we're looking for with specified complexity is two things: complexity and specification. Okay, just like the term says. All right, so specified complexity, what is the argument? The specified complexity argument says that complex and specified information is produced by intelligent action and thus reliably indicates design. It requires design. All right, so we're going to be dealing with information. And we're going to be dealing with what do we mean by complexity? How can we, not really what do we mean by complexity, but how can we tell something is complex? What makes something complex? And then what makes something specific enough to say that this had to have been the result? Well, if I'm an intelligent design proponent, I would say an intelligent causation. But I'm not. I'm a creationist, so I'm going to say God, okay? But what is it about living things that allows us to say somebody, and in the case of creation, God designed it? And we said in our creative design argument that creative design, we said that God's hand, or God's creative hand in particular, is obvious in nature. It's obvious in nature. So we're going to use specified complexity to nail that down in a scientific manner. Specified complexity. Okay, a system or sequence is complex if it is unlikely, and it's specified if it matches an independent pattern. So we all know what complexity is. The goal here is, how do we tell something is complex? How do we're going to use the word detect a lot today. How do we detect design? Or as William Dembski put it, how do we make an inference to design? So specified complexity. And we're going to be dealing a lot with information. In fact, a lot of times in intelligent design literature, you'll see CSI, and that is complex specified information. So complex and specified information is produced by intelligent action and thus reliably indicates design, or it can be used to detect design. So we can say God's hand is obvious in nature, and we're going to give a means to show that it's obvious in nature. So this is developed by William Dembski. So we're going to talk a little bit about him. William Dembski, he is a mathematician and a probability theorist. He is an MIT graduate. He has a PhD in both mathematics and philosophy. Here's his argument put out in his book, The Design Inference, published 2 years after Michael Behe's book, Darwin's Black Box, 1998. Okay, and this is where he is formulating the specified complexity argument. He's applying it to information, and he's saying we can detect design by making a design inference. We're going to say that God's hand is obvious in nature, and we're going to use William Dembski's argument to show how we can say that. So William Dembski, first of all, his first argument is that rational agents, that's us, human beings, we will detect the activity, the prior activity of other minds or intelligence by the characteristics of the effects they leave behind. So we can detect prior activities caused by intelligence by the effects, those, whether it's a sequence or it's an event or it's an object. We can detect the effects of intelligence by the characteristics of those effects. All right? And this is done all the time in science. The argument or the criticism that William Dembski gets for this argument is the fact that we don't use this in science. Well, yes, they do all the time. And we use it all the time. We detect intelligence all the time. This is kind of a fancier statement of William Pauli's argument back in the 1800s. What was William Pauli's argument? It's the watch. If you find a watch, you know it didn't just come, it's not a natural occurrence. It was designed by the watchmaker. So this is kind of the same argument, but presented in a more logical and even mathematical way. So the design inference, the first part of the design inference that William Dembski is putting forth in his specified complexity argument is that rational minds, rational agents, people, often detect the prior activity of other minds, which is intelligence, by looking at the characteristics of what they leave behind. All right, so this is done all the time in science. Scientists use this all the time, especially in the field of forensics, in the field of archaeology, cryptology, and even the SETI program, which is a big waste of money. But what is the SETI program? Search for extraterrestrial intelligence. And how do they search for extraterrestrial intelligence? Well, the same way that we can infer design from living things. All right, so the second thing that he argues is that the effects of intelligence are both recognizable and distinguishable from the effects of natural causes. Back to the watch. We can distinguish a watch from a rock. We can distinguish a watch from random things that we find in nature without any intelligent cause. So the effects of intelligence are both recognizable and distinguishable from the effects of natural causes. And he gives us what he calls his design filter, or his explanatory filter, of how we can actually distinguish the effects of intelligence from the effects of natural causes. And the whole crux of evolution is that there is no God, he didn't create, or if there is a God, he didn't create. The whole crux of evolution is that God didn't create, so natural causes have to explain the origin of everything. So if we can show that natural causes things are too complex for natural causes to have produced them. That's the crux of this argument. Things are too complex to have been the result of just natural, and especially natural random processes. And that's the whole crux of evolution. So the effects of intelligence are both recognizable and distinguishable. All right, here's I'm stuck on Michael Behe. Here's William Dembski's, another book of William Dembski's, another book that he called No Free Lunch. Okay, no free lunch. Specified complexity. You can't buy specified complexity without intelligence. So he continues his argument with the idea that a system or sequence that has the joint properties of high complexity and specification invariably result. Any system or sequence that has these properties invariably results from intelligent causation. Okay? There's the two characteristics: high complexity, specification. Okay, so if we see high complexity and specification, it, what does he say, invariably results from an intelligent cause. So we start looking for those two things, complexity and specification. And then we're going to talk about how we do that, and that's what William Dembski calls his design inference. How do we look for those properties? How do we distinguish something that is a result of intelligence from something that is the result of natural processes? And we can apply that then to how do we distinguish something that was created from something that was just here over millions of years by random processes. So the idea here is that it's a reliable way to infer design. Okay, so all of this that we've just discussed, okay, we can recognize and distinguish the effects of intelligence from two things: high complexity and specification. That's the foundation of the specified complexity argument. So there they are. What are the two requirements of specified complexity? What are the effects that we're looking for? If we say that we can infer design by looking at the effects produced by intelligence, then what are we looking for? And how do we say something is highly complex? Well, according to William Dembski, high complexity, which is an effect of intelligence, is noticeable or detectable by low probability. So if an object, event, or system, or sequence is complex, it's unlikely. Remember, William Dembski is a mathematician. He's dealing with probability. Michael Behe, what did he attack? Accumulation of numerous, successive, slight modifications. William Dembski is going to attack the idea of randomness. Keep in mind, we're talking about Darwinism or neo-Darwinism or gradualism. Those ideas are synonymous as far as we're concerned. And remember, there's three steps: mutations, and according to Darwin, he called it variation by random chance. So we are directly attacking step one of gradualism this time. Michael Behe and irreducible complexity, we were directly attacking step three, accumulation of small changes. Do you understand that? Are we attacking step two? Okay, we've got to think this through. Remember, with the intelligent design proponents, a lot of them are still evolutionists. And their argument with evolution is not that it occurred, it's the mechanism of gradualism or the mechanism of Darwinism. What are the three steps of neo-Darwinism or gradualism? Step one is mutations, which are random events. Darwin said variation by random chance. Step two is natural selection. Step three is an accumulation of small changes. Correct? All right, so Michael Behe attacked step three. He said we can't explain irreducibly complex systems with numerous, successive, slight modifications. Now, William Dembski, we're going to use William Dembski to attack the first step, randomness. What is Michael Behe? He's a biochemist. He was looking for steps in evolutionary processes, or biological processes. What's William Dembski looking for? He's looking for the chance of it occurring. He's looking at probability. William Dembski is a mathematician. So William Dembski is attacking step one, variation by random chance, of course, which we know now are mutations. Are we going to attack step two, natural selection? No. Why not? Why not?
They still believe it since they still accept the evolutionary.
Well, yes, they still believe it. They still believe all three. Oh, I see what you're saying. The intelligent design proponents still believe evolution. That's true, but that's not what I'm getting at. Does natural selection occur? Absolutely. Remember, microevolution? There is variation within kinds. Can we observe natural selection in nature? Yes. We're not attacking natural selection. Natural selection is observable in nature. Natural selection, though, cannot explain origins. So I'm not going to attack natural selection directly. We're just going to attack the fact, we're going to say that natural selection is blind. Isn't that what we said? Isn't that one of the barriers to Darwinism? That if something doesn't function, natural selection is blind to it? It's not that we don't, I'll use the term, believe in natural selection. It's that natural selection is inadequate to explain macroevolution. Do you understand that? It's important that you understand things like this so that you can make a credible argument. So we aren't going to attack natural selection. We're just going to say that natural selection is not the same as evolution. It's variation within kind. Remember, microevolution versus macroevolution. Does variation occur? Yes. Does natural selection act on different variations? Yes. Darwin did observe that on the Galapagos Islands, didn't he? So keep in mind what we're doing and what we're attacking and what is true and what is not true, or what is scientific and what is not scientific, as much as we can. So we are going to attack step one. We're going to do it twice. We're going to attack the random aspect of it, and then we're going to specifically in the next lecture attack mutations. And we're going to use John C. Sanford and the genetic entropy argument to do so. Okay? So far we have the irreducible complexity argument that attacks the accumulation of small changes resulting in a new organism. Okay? Then today we're doing William Dembski's specified complexity, and that's a direct attack on the randomness of mutations. Then we're going to attack mutations themselves and say that mutations do not produce new organisms because they cannot produce new information, so that's called the genetic entropy argument. What is happening to the human genome? It is becoming more random. That's genetic mutation or genetic entropy, and that's what mutations do. Mutations don't give us new organisms. Mutation doesn't produce more DNA. Mutations delete DNA. If it does produce more DNA, it's going to be a random sequence, which is directly related to what we're going to talk about today. So it's important that you put this in context of what we're doing. And now I'm going to give you the details of how we can detect design, what specified complexity is, and then start applying it to living things. So William Dembski says that we can distinguish the effects of intelligence by looking for what two things? What are those two effects? High complexity, which has a low probability, and then specification, which is a recognizable pattern. Okay? So an object or event or sequence or process is complex if it has a low probability of occurring. Then a object, event, or sequence is specified if it matches an independent pattern. Here is the design filter. Not exactly the way William Dembski put it, but this is how the intelligent design proponents use their design filter. All right, so with the design filter, I'm going to get the laser pointer here. When we look at an event in the past, if we're a forensic scientist, or we look at an object that we found as an archaeologist, or if we're a cryptologist and we're looking for a pattern that conveys a message, that's what cryptologists are doing. They're trying to break a code. Oh, DNA, what do we call that? The genetic code. Okay, so we're going to apply it to DNA in a minute. So if we're looking at something, the first thing we ask ourselves is it a contingency? In other words, is it something that we wouldn't expect to happen, or is it just a natural occurrence? Is it a necessity because it's an automatic result of natural law? If it is an automatic result of natural law, then we know it's from necessity, it wasn't designed. So is it a contingency? Yes. Then we're going to proceed down our filter. If it's not, we're just going to attribute it to a natural cause or a natural chemical reaction or something like that. So if it is a contingency, then we'll go and ask ourselves about complexity. Is it complex? Remember, William Dembski says that complexity is indicated by low probability. It's not what complexity is, but complexity is indicated by low probability. So if we look at something and we know that it is not the result of random chance, it's not complex. It's a low probability of occurring, then it can easily happen by chance. Are you following me? If it has a low probability of occurring, then we can say it's easily attributable to chance. But if it has a high probability, I've said that backwards, let's back it up. If it has a high probability of occurring, it's simply chance. If it has a low probability of occurring, it's complexity. So if it's not a contingency, if it's not attributable to natural law, it is a contingency. If it has a high probability of happening, it's just chance. If it has a low probability of happening, it's complex. Then, if we can recognize it, it is specified. And so if all of these together are true, then we can infer design. We can say this had an intelligent cause. It was designed. Okay, so we're going to start at the beginning again. We look at something. Let's say we're looking at a sequence of letters, or we're looking at even an object. Is it something that could just be the result of a natural cause? All right. Is it a necessity of chemistry? Is it a necessity of physics? If so, then it's not designed. Then, does it have a high probability or a low probability of occurring? If it has a high probability, it's probably just chance. If it has a low probability, it's complex. So it's not that complexity is low probability, it's that we can detect complexity by looking at the chance of it occurring. If it has a high chance of occurring, it's just random, it's chance. If it has a low chance of occurring or low probability of occurring, it's probably complex. But then it also has to be specified. Is it recognizable? Does it correspond to a known pattern? That would make it recognizable. If it is, then we can infer design. Let's go through this a little more specifically. There's our 3 steps in our design filter. So, is it a contingency? That means it's not from natural causes. Is it a contingency? If it is, then go to the next step. Is it complex? If it is, then go to the 3rd step. Is it specified? That's the design filter. So we look at something and we say, okay, that's the result of just random molecular collisions. It's a requirement of chemistry. It's not designed. Okay? It's not a necessity. A necessity is something that's going to happen anyways. A contingency is the opposite of that. It's not something that's going to happen anyways. You understand the word contingency there? So the first step is it a contingency? Or is it a necessity? Then we'll go, if it is, then we'll ask ourselves, is it complex? There's a definition of complexity. It's the state or quality of being intricate or complicated. All right, and mathematically speaking, William Dembski tells us that if it has a low probability of occurring, we can say it's complex. So it's unlikely to be obtained by chance. It's an improbable event. So if it's an improbable event, it has a low probability of occurring. That means it's complex. Then specification means it's recognizable as a distinct, particular, and exact. So if something's specified, then it's distinct, particular, and exact. It corresponds or relates to a pattern that we recognize. It's a recognizable pattern. It corresponds to the English alphabet. Okay? That's what we're talking about here. If it corresponds to the English alphabet and it's in the appropriate sequence, we can recognize it as a word. So it's got to be both. So that's what the design filter does. It's a way to look at something and say, okay, that happened due to an intelligent cause. And we're going to say that, as a creationist, we're going to say that system, that organism was designed. It's not the result of natural random processes that evolution requires. So think about that design inference or the design filter. We're going to start at the beginning again and figure out, how does this work? The first thing we ask ourselves is this the result of natural occurrences that are going to happen anyway, or is it a contingency? If it's a contingency, then we'll proceed. If it's a contingency, we'll proceed to complexity. And we'll ask ourselves, is it complex? Well, how can I tell? There are some things that look very complex. I should have put my snowflake picture next. A snowflake is not a contingency. It happens all the time without intelligent design. So do crystals, but they have a different kind of complexity. That's why we need the third stage of the filter, specification. Snowflakes are complex, but they're not a contingency, and they're not specific. Okay, so is it complex? We're going to say, is it there a low probability of this particular sequence occurring? Then we're going to call it complex, but that's not enough. Then is it specified? Does it correspond to a recognizable pattern? If, especially these two, then it is designed. So that's the design filter that we will use to make a design inference. So these are the three requirements, or the three steps of making a design inference. We're going to ask ourselves, is it a contingency? Yes. Is it complex then? Yes. Is it specific? Yes. Then it's designed. So let's illustrate contingency, complexity, specificity, and then put that together as specified complexity. The first one, we're going to use a sequence or string of characters or letters. The first one is a contingency. It's something that can happen. If we had a monkey typewriting, sitting at a typewriter, could he come up with something like that? That's a repetitive, simple sequence. All right? It can be the result of a natural cause. It does not require intelligence. Okay? Typing this, does that require intelligence? No. Complexity. This is complex. What would be the probability of this exact sequence occurring? Pretty low. But specificity, does it mean anything? No. So it's complex, but not specific. Specificity, does that mean anything? Yes. But is it complex? No. Okay? So we have to put together both of these two in the middle, complexity and specificity. Okay, contingency is kind of the first step of the filter, just to pop it out of there right away. But to really make our design inference, we have to look for complexity and specificity acting together. They have to be joint properties. So when we put specified complexity together, we get both complexity and specificity. These is a recognizable pattern. It corresponds to words of the English language. That gives it meaning. And when a message has meaning, it comes from an intelligent causation. That's what the SETI scientists are looking for in signals, radio waves from outer space. They're looking for patterns that indicate intelligence. They're looking for specific patterns, not just random noise. This is random noise. Okay? This is complexity, but it has no meaning. So we have to have both of these, and this has meaning but no complexity. Do you see? So we put the two together, call it specified complexity, and then we can make our design inference. So complexity alone does not require intelligence until specification is added. Could a monkey on a typewriter type a few no's here and there? Sure he could, but it's not complex. All right, so we have to put both ideas together to be joint properties of a sequence or an event or an object. Okay, so specified complexity is evidence of design, and we will use it then to make a design inference. I keep saying design inference. Inference is a word you probably don't use a lot. So what is an inference? An inference is a conclusion derived from evidence or fact. So when we're making a design inference, we're making a conclusion by looking for complexity and specificity together. So an inference is a conclusion made by looking at the effects. Are those effects complex and specified at the same time? So to infer is simply to draw a conclusion. So we are going to conclude design by looking at the evidence of complexity with specification, both together, specified complexity. Do you see why the argument is called that? Specified complexity. We have to have both complexity and specification at the same time before we can say that had an intelligent causation, whether it's a sequence or a process or an object or an event. So when we are making a design inference, we're talking about drawing the conclusion of design by looking at the effects. The effects have to be both specific and complex. There's two steps in making a design inference or any inference. We're going to recognize the effects of intelligence. By now you should know the two effects of intelligence. What are they? Both complexity and specificity. Okay? So we look for and we can recognize the effects of intelligence. So we're looking for a highly improbable arrangement. If we're a cryptologist, we're looking for a highly improbable arrangement. And then we're looking for a recognizable pattern. Where are we going to find this in nature? Where's the information stored for living things? Where is it? In the DNA of every cell. So we're going to be applying this to the DNA. So we can recognize the effects of intelligence by looking for a highly improbable arrangement and a recognizable pattern. Will we find those in DNA? Can we make an inference to design by looking at the DNA found in living organisms? So we will. We're going to draw the conclusion. We're going to make an inference that there had to be intelligent causation. However, I am a creationist, so I'm going to say we're going to draw the conclusion. We're going to make the inference that God designed everything we see in nature. And this is simply a cause-effect reasoning. We see a cause, we can't see the cause, so we see an effect and we look back to the cause. So we see complexity and specification, we know the cause was intelligence. It's a cause and effect relationship. All right. William Dembski received a lot of criticism, as you can imagine, for this. Why? Because he had a logical way to approach the question of, was this designed? Did God create it? Or is it just random evolutionary processes? All right, so is this something that is done in science? Is this something that is a logical technique? Yes. Making an inference to design is commonplace. Most of the time it's obvious. Back to the watch. You find a watch, you don't think it's something that happened in nature. It's not the same as finding a leaf or a rock. Okay, so remember, we're going to now take William Dembski's argument and we're going to apply it to creative design. God's hand in nature is obvious. That's because design is obvious. We see design and recognize it every day. And scientists also frequently make design inferences, whether it's archaeology, cryptology, or cryptography, or the SETI project. Let's just do a simple one. I see that on the ground. Is that a improbable event? Does that rock have an improbable arrangement or any properties that are improbable? No. Does it have a recognizable pattern? No. I'm going to walk right by it. I will not notice it. But if I'm an archaeologist, oh, that's not animating for me. Hold on a sec. I have a picture of a pottery that's supposed to animate on top of that, and it's not going to do it. There it is. Okay. Sorry, technical difficulties. All right, so if I'm an archaeologist and I see that, what am I going to infer? It's from some civilization somewhere. Somebody made that pot. I certainly couldn't make that pot. Okay, so it is an improbable arrangement and it's recognizable. What about that? Is that an improbable arrangement? Is it a recognizable pattern? There's a difference between finding a rock and finding an arrowhead. There's a difference between seeing some type of rock formation and finding that clay pottery. Many times you'll see, as an illustration, you'll see Mount Rushmore. Mount Rushmore, sorry. Mount Rushmore is a improbable event, and it has a recognizable pattern. You recognize who's on there. George Washington, Thomas Jefferson, Abraham Lincoln, and Teddy Roosevelt, right? Okay, so do we make inferences to design every day? Are they commonplace? Yes. Okay, so let's apply specified complexity. We can apply it to systems. We just did with the pottery and the arrowhead. We'll look for a highly improbable event or object and a recognizable pattern. There they are. Complexity followed by specificity, the specified complexity argument. We can apply it to sequences. We can look for a highly improbable arrangement. What's that? Complexity. And of course, we're going to look for a recognizable pattern. Does that arrangement of letters spell English words? That's a recognizable pattern. Or it doesn't have to be in English. It can be in 3 letters, or actually 4 letters. What are those 4 letters? A, T, C, G. You recognize those 4 letters? A, T, C, G. Adenine, guanine, cytosine, and thymine. Those are the 3 nitrogenous bases that make up the DNA molecule. Okay, and then will we find them in a particular sequence? Yes, we will. They're called codons. They're in groups of 3 that form words, just like we can take the 26 letters of the English alphabet and form words. They code for particular amino acids in a protein sequence. Okay, so if a sequence displays specificity and complexity, we know it's not random. That makes it convey a message. That means it's the result of intelligent, and what do we call it? Information. So what we're going to do is we're going to apply, and what Stephen Meyer, especially, along with William Dembski, has done with specified complexity is applied it to information. And the question is, what is the origin of information? So if a sequence displays both complexity and specification, then we know it is not random. We know that that's how it conveys a message. We know that it required intelligence to put it together, and we call it information. So when a sequence of letters is not random, follows a recognizable pattern, meaning it's specified, then we know it's the result of intelligence and it conveys information. So, can we find specified complexity in living organisms? I've been ahead of myself and told you that we do, and we find it in the DNA molecule. Stephen Meyer, we've had him before. He is the co-founder of the Discovery Institute, and he is a PhD in the philosophy of science, and he's taken William Dembski's argument further and applied it more specifically to the information found in DNA. Okay, let's review. DNA is a highly complex molecule. Its name is deoxyribonucleic acid. 1953, famous pair, Watson and Crick, were able to publish their findings, and they discovered the double helix arrangement of the DNA molecule. And this is the molecule of genetic information. So the question is, what is the origin of DNA? Which is the same as asking, what is the origin of information? So here's where we can apply specified complexity to creation, to origins. Is this the result of intelligence? Was it created? Was it designed? The genetic code is called that because it is a code. It conveys a message. It is information. So that means it had to have been the result of intelligence. Remember, complexity implies design. What does information require? Intelligence. To convey a message requires intelligence. A message is characterized by complexity and specification. It's complex and it's in a recognizable pattern. Both of those are required to convey a message. Is a message conveyed by DNA? Okay, it is literally a 4-character digital code. Adenine, guanine, cytosine, and thymine. These are arranged along the rungs of the ladder. They're paired along the rungs of the ladder that make up what we call the double helix, DNA. There's the DNA molecule. Is that a highly improbable arrangement? Took Watson and Crick, I don't know how long they spent on that project, but they won the Nobel Prize for it. Okay, it's a highly improbable arrangement. It is complex. Then the question is it specified? Does the arrangement of those 4 bases convey a message? And the answer is yes. DNA exists in triplets called codons, and each codon literally represents a particular amino acid, because DNA is used to produce proteins. And remember those biological processes that we looked at yesterday? We had the complement cascade. What was that? 9 very specific proteins. We had the blood clotting cascade. What makes up the blood clotting cascade? Numerous, highly specific proteins. Where are proteins produced in the cell? How are proteins produced in the cell? They're produced from DNA. DNA conveys the message of which amino acids are put in what order to make this particular protein. So there is numerous, infinite almost, not infinite, but nearly, as far as we're concerned, amount of information found in DNA. Every one of your cells has 46 chromosomes, which is 23 pairs, because you do have an extra copy of everything. But let's just take those 23 of them, one of each pair. How much information is on your 23 chromosomes? Everything needed to build every part of your body, all of your proteins. You think about proteins, you should think about your skin, right? Skin and the fibers that make your skin elastic, elastin and collagen. Your muscle tissue is made up of two types of proteins called actin and myosin. Your hair, what is that? It's a protein called keratin, and I'm being very simple. So, is there information found in DNA? Yes. Okay, more information in DNA than in a whole library. In this whole library, definitely. Okay, so what is the origin of that information? Because that information is both complex and specified. That means it had to have been the result of what? Intelligence. So here's our conclusion. DNA could not have evolved from natural random processes. The idea of specified complexity is the direct result on the randomness. So we're going to say that the origin of information is not from mutations in the DNA. It's impossible. Mutations are random. So DNA could not have evolved from random processes. It's a highly improbable arrangement and a recognizable pattern. Okay, in graduate school, I had to learn the 20 amino acids, and I had to learn the codons for each one, along with the stop codons and the start codons and other regulatory codons. Very complicated, okay? So DNA is a genetic code. It conveys a message. It is information, and its evolution is impossible. It had to have been designed. That's the crux of the specified complexity argument. That's how we're going to attack evolution or gradualism, is the idea of randomness. Random natural processes cannot explain the information in DNA. That's the conclusion. Random natural processes cannot explain the information, the origin of the information in DNA. All right, and we're going to pick that up and expand upon DNA with the genetic entropy argument next week.